Okay, so you can refer to ULearn in chapter 3, free vibrations, and you can read all the introductions in the ULearn yourself. Okay, so what you have learned in the previous chapter, which is free vibration, is from here, from free vibrations. What you did is you derive K equivalent, M equivalent, and C equivalent, and from here you can have the natural frequency. So this one we call it undamped natural frequency. Okay. If there is damping, then you can find the damped natural frequency. Which is, this one is the same, omega n, is omega n. And the damping loss factor, you have done it already in section damping loss factor. In section 24, if I'm not mistaken, or 25. Yeah. But damping loss factor is usually very small, 0.1, 0.01, 0.2. Even if it's 0.2, let's say, it's too big for damping loss factor. It's already a large value. So 0.2 square, and then you will end up with 0.04. So 1 minus 0.04 is almost the same as 1. So damped natural frequency and natural frequency is almost the same. Okay, so what is the context of free vibration? So let's say you have a structure, you have a piping. And let's say this section of piping is supported by spring, and also here supported by spring. So you can we have the flow of the fluid in that direction. Okay, so let's assume because of the flow of the fluid, the piping is vibrating vertical. Yeah, the piping is vibrating vertically. Let's say the amplitude is xt. Yeah, so you can imagine the piping is vibrating vertically because it's supported by a spring, so it's quite flexible. And you know the mass of the piping, including the fluid, and you know the stiffness of the damper. Yeah. So although there is no fluid inside the piping flowing, so from here, can we know the natural frequency? We know K, we know M. So this piping actually has already the natural frequency. Eh? So omega n is K, which is together with this K, it should be K total. So K1, K2. So assuming everything in phase, so K total divided by M square root. So then you have the natural frequency of the piping. Now, if the fluid, if we let the fluid flow inside the piping, okay, and the fluid can have different velocity. Okay? The fluid can have different velocity, so different velocity will generate different frequency. Okay, so the fluid will excite the vibration of the pipe with different frequency. So let's say omega, or maybe 2 pi f. So this one is frequency of the fluid. Yeah, so related to the speed of the fluid, which then generate the vibration of the pipe. So the pipe will vibrate according to this frequency. Yeah, so because the pipe is forced to vibrate with the frequency of the fluid, then that's why we call it forced vibration. We call it forced vibration. So the question is that what happens if the fluid, if the flow of the fluid, the frequency is the same with the natural frequency? So this is where the interesting part happen. Okay, so let's model this system in mesh, spring and damper model. So we have the mesh, of the pipe, we have the total spring. Yeah, so just for the sake of, we make it simple, just put it K. So the pipe will vibrate in vertical. So xt is the amplitude of the vibration of the pipe. Okay, and there is a force from the fluid. Okay, so there is a force from the fluid, is Ft, which force the mesh and damper of the system to vibrate. So what happened with free vibration before? Free vibration before is we don't have any fluid inside the pipe. So the pipe and the spring. So what happened is we push the pipe. Yeah, we push the pipe and we let it go, and the pipe will vibrate. Yeah. So that's the free vibrations. If we have damping, then the pipe eventually will stop it. If no damping, let's say ideally no damping, but ideally everything will have damping. But if no damping, then the pipe will vibrate, will go on to vibrate without stopping. So that's free vibration. So there is nothing that forcing the pipe to vibrate. The pipe is vibrating at its natural frequency. In free vibration, the pipe is vibrating at its natural frequency. So this one is free vibration. Okay, so now if we let the fluid flow inside the pipe, and the pipe will vibrate according to the speed of the fluid. Yeah. So if the fluid, the speed is low, then the vibration of the pipe will also be low frequency. Okay. So we have this mesh spring and damper model. So from here we can derive the equation of motion, m x double dot plus ax equals to, previously equals to 0 in free vibration. Now we have the force there. So equals to Ft. So let's assume the force is sinusoidal. Let's assume the force to be sinusoidal. So let's make it this one f small. So let's assume the force to be sinusoidal. Okay, which is in piping is not sinusoidal. It should be random, but for the sake of in order for you to imagine what happened. So let's say so what does it mean by sinusoidal is that the functions of the force will be sinusoidal. Okay, so so it forced the piping to vibrate. So this going up, going down, going up, going down, going up, going down. Right? That's sinusoidal. Okay. Now, if the force is sinusoidal, yeah, if the force is sinusoidal, and what happened with the response, the vibration of the pipe? Yeah, so this is the force from the fluid. What is the response of the pipe? So the pipe will follow whatever the force exciting the pipe. So if the pipe is excited by the sinusoidal force, then the response or the vibration of the pipe will also be sinusoidal. So xt will also be sinusoidal. Yeah, the structure will follow whatever the excitation force given to that structure. So then we can substitute. We are clear. We are now clear with the physics. Okay, we are now clear with the physics. So then in mathematics we can substitute this to the equation. So m, what is x double dot? X double dot is second derivative of x. So the first derivative will be, what is the first derivative of x? So omega x cos omega t, and then we differentiate one more. So omega will be out, but cos will be minus sine. So omega square x sine omega t. Okay. So then substitute, yeah, we substitute x double dot here. So you put it there. Plus k x sine omega t here, yeah. So this x, put it here, and then we have f sine over t, f sine omega t. Okay, so I can cancel out sine, sine, sine. So we end up with I want to put this one in the front. Okay, x equals to f, right? So x equals to f is 1 over k minus omega square. So we have this equation here. Okay, so what is this equation telling us? This is the most important. So this one is just mathematics, but that mathematics will tell us something. Okay, so let's see if we want to express this one in terms of natural frequency. Natural frequency. Can we put natural frequency here? So we will divide it on the top and the bottom with k. So 1 over k. The bottom we also divide it by k. Yeah. So then you have 1 over k. This one you have 1. Remember natural frequency square is k over m. So m over k is 1 over omega square. So now here you have m over k, right? So omega over omega n squared. Okay. So these equations we have here. So x over f, we want to plot it in the graph because we want to see what happened. So x over f is what? X is the amplitude of vibration. Force is the force, the unit, the force that excite the pipe. Yeah. So the force from the fluid exciting the pipe. So this one tell us is the vibration amplitude over a unit force. Yeah. How millimeter per Newton. Yeah. If we give 1 newtons, what happened with the amplitude of vibration? Yeah. So the unit of amplitude over unit of force. Okay, so we want to plot it in terms of frequency, and here because of vibrations, we don't care whether it's the piping is going up or going down. What we interest is the amplitude. Yeah, the amplitude here. Yeah, so what we interest is this amplitude. We don't care whether it's going up, it's going down, but what we interest is the amplitude around the equilibrium. So if this is equilibrium, so we interest on the amplitude of vibration. So then here we put it absolute. If it is negative, it becomes positive. Yeah? Yeah, so this one is absolute whole thing. Okay. So now, what happens if the fluid? So remember, omega is the frequency of the fluid. Eh? Frequency of the fluid which vibrate the frequency of the pipe. Yeah. So frequency of the fluid or frequency of excitation. Frequency of excitation. And also the frequency of the pipe. Yeah. I want you to remember this concept. Where is the frequency coming from? Yeah. So it's the frequency because of the fluid flow, and that fluid flow will vibrate the pipe. Yeah? So it's frequency of vibration of the pipe as well. So what happens if the frequency is much lower than the natural frequency of the pipe? Remember, the pipe has already the natural frequency, which depends on the K, which depends on the structure of the pipe. What is the stiffness of the spring? What is the mass of the pipe? And the mass of the fluid and everything. So it has its natural frequency. So what happens if the fluid flow, the frequency of the fluid is much lower than the natural frequency of the pipe? Yeah, the frequency of the fluid is much lower than the frequency of the pipe. So what happened with x over f? We have to go back to the formula. If omega is much lower than omega n, let's say omega is 0.001, and omega n is 1000. So 0.01 divided by 1000 becomes 0.00 something. So 1 minus 0.000 something is 1. So what we have is at low frequency is 1 over k. And the vibration of the pipe over a unit force is 1 over k. So low frequency is somewhere around here. So let's say we have the natural frequency somewhere around there, at the natural frequency of the pipe. So low frequency maybe somewhere around there, low frequency. So what mathematics tell us is in low frequency, the amplitude x over f is 1 over k. So 1 over k, let's say put it there, 1 over k. So along the low frequency, it's 1 over k. Okay, something like that. Okay, so what happened when omega equals to omega n? when omega equals to omega n, meaning the speed of the fluid, the frequency is the same as the natural frequency of the pipe. We don't know. Sometimes in practice, when you have the fluid flow, you can adjust the speed, and when the speed is exactly the same as natural frequency, so that's what happened. So what happened when omega over omega n? Here you can see omega over omega n. When omega equals to omega n, then you have omega n over omega n. So so you have 1 here. 1 minus 1 is 0. So 1 over k over 0 is, so 1 over k over 0 is infinity. So at natural frequency, exactly at here, what you have is, when the frequency is approaching the natural frequency of the pipe, then the vibrations will go very large, infinity. So what does it mean? What does it mean? X over F goes to infinity, meaning X will be very, very large. The vibration will be very, very large over unit force. So you give 1 Newton force, the vibration will go to infinity at natural frequency. So this is what we call resonance. This is when disaster, when you see the Tacoma Bridge in the US vibrating like hell. It's a massive bridge, but the wind is just a simple wind. It's not a typhoon. It's just a normal wind flowing on the river, can destroy such a massive bridge. So this is the phenomenon of resonance. So it doesn't need the wind to have high force, but the wind to have the same natural frequency with the bridge. Okay, and then what happened at high frequency? What happened at high frequency? So when omega is larger than omega n, so let's say this one 1000, or this one 1 million, and this one is 1, so much larger. So omega is 1 million, this one is 1, so 1 minus 1 million. How's that? 1 minus 1 million is minus 1 million. So we can ignore 1 because 1 is too small according to 1 million. So it's minus 1 million, which is minus the whole thing. So because we have bracket here, absolute, so then we have positive. We have a positive value. So 1 over k over omega square over omega n square. All right. So you know omega n square is m over k. So 1 over k. Omega n is, sorry, k over m. K over m. So then you can cancel out k, cancel out. So you end up with 1 over m omega squared. So at high frequency above natural frequency, if the fluid flow is high frequency above the natural frequency, so what happened? Amplitude over unit force is the functions of the mass, the inverse of mass and frequency square. So meaning if you increase the frequency, x over f will be smaller. Increase again the frequency will be smaller, smaller, and smaller. So at high frequency, if you increase the frequency, when you increase the frequency, so high frequency here, high frequency. So when you increase the frequency, the vibrations will go very low, approaching 0. Okay, so this is where you end up with the graph of x over f. We call it transfer function. vibration is the function of frequency. Okay, any question? Okay, tak ada soalan. Baik. So, in the activity, you have to solve that activity. So let's see the first activity. Let's see the first activity. Learn. Pulse vibration, undamped pulse vibration. Okay, so let's see the first activity. Yang ini nanti boleh tengok So this one is you can watch yourself. The same explanation as what I've explained it to you. Yeah, here. Experimental table is located on the floor. So this one, we have the table and we have the nearby rotating machine running at 800 RPM, 800 RPM. The vibration machine is effectively transferred to the table and the steady state vibration is measured to be 12 millimeter per second. Vibration of table is 12 millimeter per second, the amplitude, 12 millimeter per second. What is the vibration velocity of the table? Anyone can answer? What is the vibration velocity of the table? The answer is already there. You can type it in the chat. Yeah, so it's to be 12 millimeter per second. Okay, so what is the vibration frequency of the table? What is the vibration frequency of the table? So remember, the table is vibrated because of the rotating machine. So the vibration from the rotating machine is transferred to the table. So the table will vibrate because of the machine. So what is the vibration frequency of the table? Okay, what is the vibration frequency? Ya, 800 divided by 800 divided by 60. 800 divided by 60 is 13.3. Yeah, that's a vibration. RPM divided by 60 is already hertz. 800 divided by 800 divided by 60, 13.3, yes, hertz. Yeah. If you want to radian per second, you have to multiply by 2 pi. Okay. So here, activity 3 to 1, you can do it yourself, but the idea is, you know the mass of the bar, yeah. So you know the stiffness of each spring. From here, you can calculate the natural frequency. Yeah? What is natural frequency? But the bar is excited with 4 Newton, frequency 1 Hertz. So assume rigid body. So now the vibration of pipe is in phase. All the spring is in phase. Does resonance occur? So you have to prove whether this one is resonance or not. Yeah. So it's very simple. Now I want to discuss this one a little bit here, because this one you have to do it yourself. 3 to 2 and 3 to 3. Yeah? 3 to 1 and 3 to 3. Okay. So this one here, I have already the video, my explanation to the other section, section 78. So I will share with the video, then you can watch my video carefully how to deal with this one. But the idea is, let me share again my iPad. In the free vibration, so you have the bar, and let's say this is the center of rotation here. Yeah. So you know the second moment of inertia of the bar, M, and maybe you have the spring here. Maybe you have the spring there. And we want to use the displacement of the spring at the end as generalized coordinate. So this is generalized coordinate. Okay. So in the free vibration, what you did is you find the J M equivalent, yeah, from the kinetic energy. X1 is generalized coordinate, and then you find the potential energy. So now you find the K equivalent. X1 is generalized coordinate. So from here you can have equation of motion, M equivalent X1 double dot plus K equivalent X1 equals to 0. So this is free vibration. The previous chapter, free vibration. Now if we have the force, let's say the force is excited at that location. So what happened with the equation of motion? Is it simply Ft? Is it simply Ft? Yeah. So what happened if Ft is not here? Ft is here at the end of the spring. Or what happened if Ft is here? So we cannot just put Ft straight away, yeah, because Ft can be in different location. If Ft is here at the locations where you measure the generalized coordinate, then you can put it straight away, Ft. Yeah, if Ft is exactly here. Because when Ft is actually here, then you can do the mass spring model. So this one is M equivalent. You have K equivalent. and then you have x1 as the generalized coordinate. Then you have ft. So that will be straight away the equation of motion. But ft is not at that location. ft is at different location. So what we do is we have to make a virtual force as if the force is here. So if the force is here, what is the amount of the force? So the amount will not be the same as here. Okay, so as if there is a force in here, let's say the force is F2. Let's say the force is, don't make it F2. Let's say the force is F accent P, something like that. So what is the amount of that force? Okay, so we can the force here will contribute the moment at O. The force here, the original force, will contribute the moment at O. So if we want to replace the force here to be here, then that force should contribute the moment the same at point O. Yeah, so you get me? So then what is the moment at point O because of the original force? What is the moment? The moment, yeah, the moment at point O. So remember, the moment is, if we have the force, yeah, then you have the length of the bar. So the force, the moment is F multiplied by L. Concept of moment. So the moment here is F multiplied by that length. So let's say that length is L over 4. So then F multiplied by L over 4. Yeah. So what is the moment if we want to replace that force to be here, another force, but the position is here. So what is that Ft, F accent T? So the moment contribute to the center of rotation should be F accent T multiplied by, say the the length here is L over 2. So that should be F accent multiplied L over 2. Yeah. So what is F accent then? So you can cancel out L, cancel out L. Then 2 will be there. So F accent is half F. Yeah. So then this is where you put the force in the equation of motion. So that one should be F accent T. Yes, F accent T, which is equals to a half F. Okay. So remember again, Ft, we should put it the same at the location of the generalized coordinate. If generalized coordinate here, then put it there. So this is the first method. The first method, equal moment. The second method is using theta as generalized coordinate. Using theta as generalized coordinate. Even though the question is x1 is generalized coordinate, but first we have to find J equivalent and also K equivalent because theta is generalized coordinate. So from the kinetic energy, you can find J equivalent. cos theta is Jonas coordinate, and you can find the torsional K equivalent. Theta is the Jonas coordinate. So from here you can find the equation of motion. So J equivalent theta double dot plus K equivalent torsional theta equals to, now this one should be moment at point O. Should be the moment at point O. What is the moment at point O? At the location of rotation. So we have the force here. So the force multiplied by L over 4. So that one should be F multiplied by L over 4. Okay, so the equation of motion is correct already, this one. But we want x1 is Jonas coordinate, so you have to replace theta as x1. So what is the relation between x1 and theta? Yeah, so this one is x1, this one is theta. What is the length? L over 2. So L over 2. So x1 is L over 2 theta. Okay. So what is theta in terms of x1? Theta is 2x1 over L. Okay. So if we differentiate 2 times double theta, so then we have to differentiate x1 double time, 2 times again. So then you can substitute here, and then you can substitute here. So now everything will be in x1. So then you can multiply right side. You can find that using method 1 and method 2, you will end up with the same results. Okay, so this is how to solve this one, activity 322, 322, and 323. Okay, so please do it this one yourself, or you can discuss online with your friend. I will put the deadline to be at 5 or at 3 p.m. Boleh? Tak apa, saya letak lama sikit. Okay, any question? Kalau tak ada, kita cukup. So, selamat bekerja. Tak ada soalan? Malam di quiz kan?